Today we will discuss the critical sensitivity parameter that govern blast furnace operation. Our objective is to understand how various factors influence productivity and coke rate. So the fundamental goal is to maximize productivity, which is achieved only when gas flow rate is at its maximum. Simultaneously, we aim for lowest possible coke rate by improving in-process efficiency and using coke substitute. This analysis will quantify this relationship to optimize performance. So gist is that if we could able to put on our activity in such a way where we improve the process efficiencies and reduce the coke rate, then that these two components in supplement each other. However, it can gives us a maximum result. So let's begin with the blast parameter, the primary drivers of the process. Blast temperature. Now, as we know, increasing hot blast temperature is highly effective. An increase of 100 degree can decrease coke rate by 2 to 2.5% and increase productivity by 1 to even 7%. So, other sources note a coke rate reduction of 7 to 7.5% and a productivity increase of 2 to 3% for the same temperature change. Another source shows a 2.2% coke rate decrease and a 1.7 productivity increase. Coming to the oxygen enrichment, enriching the blast with the oxygen boosts output always. A 1% increase in oxygen can raise productivity by 1.5 to 3%. However, this can also increase coke rate by 0.4%, which is caused due to lower optic temperatures. Blast moisture. Now, moisture in the blast consume energy, we all know. For every 1 gram per normal meter cube of moisture added, the coke rate increased by approximately 0.82 kg per ton of hot metal, which is a good value. Now coming to the top gas pressure, high top gas pressure improves gas utilization. Increase it by just zero point 0.1 atmosphere can increase productivity by 1 to 1.5% and decrease the coke rate by 0.5 to 1%. Now coming to one of the most important aspects in our next slide, which is about a auxiliary fuel injection, which is very crucial for replacing expensive metallurgical coke. The most common injecting is our PCI, and injecting 1 kg of PCI per ton of hot metal replaces around zero point 0.7 to 1 kg of coke. Another source indicate replacement ratio of zero point 0.9 kg of coke per kg of coal. Now let us see what happens to natural gas. This has a high replacement ratio. Injecting 1 kg per ton of hot metal can replace 2 kg of coke when measured by volume. 1 cubic meter of natural gas replaces 0.7 to 1 kg of coke. Now coming to the oil and tar, injecting 1 kg of oil, um, this also can able to replace 1 to 1.4 kg of coke, and this is also important. We should not leave coke oven gas. Using 1 cubic meter of coke oven gas per ton of hot metal saves between zero point 0.4 to 0.45 kg of coke. Now coming to the body quality, actually I switch over the slide in advance. The quality of our iron bearing material, as we know, it is a foundational to a stable and efficient operation. Now Fe content high means there is a always benefit. So a 1% increase in Fe content in the body decrease the coke rate by 0.8 to 3.3% and increase productivity by 1.5 to 2.5%. As for sinter and pellets is concerned, composition of the body always matter. But however, increasing sinter in the body by 10% can decrease the coke rate by 4 to 5% and increase productivity by 4%. And as far the fines is concerned, they are very detrimental to permeability, as we all know, which are especially less than 5 mm. And here we are discussing the fines, especially in which signify the granulometry of lesser than 5 mm size. and once it increases by 1%, it kills away our coke rate, and our coke rate have to increase by 0.5 to 0.8%, and our productivity at the same time also decrease by 1 to 2%. As far the raw fluxes is concerned, it always kills our coke rate, and 10 kg raw fluxes addition leads to always increase of coke rate by 3 kg. Coming to the burden quality part 2, where we have our coke, and coke serves as a fuel reductant and a structural support for the furnace, is known to everyone. Its quality is non-negotiable as it has a multi-function, and as far the coke ash is concerned, ash is an impurity that generates slag, and at the same time it consumes a lot of energy also. So a 1% increase in coke ash increase the coke rate by 1.3 to 2.5% and decrease the productivity by 1.3 to 2%. As far coke micum is concerned, micum 10 if we talk about, and which symbolizes the resistance to degradation, a 1% decrease in micum 10 index indicating better strength, and can decrease the coke rate by 2.5% kg, 2.5 kg per ton. I want to correct it, a 1% decrease in micum 10 index indicating better strength always, and can decrease the coke rate by 2.5 kg per ton hot metal. Conversely, improving coke stability by 1 unit can save 8 kg of coke and increase productivity. As far sulfur in coke is concerned, sulfur must be removed via slag, and a 1% increase in coke sulfur increases the coke rate by 1.2 to 1.5 kg per ton of hot metal. Now coming to our hot metal chemistry, which is ultimately the goal. So controlling the final product and maintaining its chemistry is key to managing energy consumption. As for silicon in hot metal is concerned, it is a direct indicator of a thermal state, and a 0.1% increase in silicon increases the coke rate significantly by around 6 kg per ton of hot metal and decrease the productivity by 2%. One source suggests a major productivity drop even to 4% for a 1% increase in silicon. As far sulfur is concerned, targeting a lower sulfur require always more energy, and decreasing sulfur by 0.01%, we have to apply fuel, and in terms of coke rate it is 1 kg per ton of hot metal. And as for now the manganese and phosphorus is concerned, these elements also has got an impact. A 0.1% increase in manganese increase the coke rate by 0.2%, while a 0.1% increase in phosphorus increase it by around 1.3 kg per ton of hot metal. Now managing slag and tramp element is also vital for efficiency. As far slag volume is concerned, excess slag consume thermal energy. A increase of 10 kg slag per ton of hot metal increase, the coke rate has to increase 2.5 to 3 kg and can decrease productivity by 0.5%. Alkalis, zinc and lead, these elements are highly detrimental. They recirculate in furnace, degrading in coke and impairing permeability. An increase of just 1 kg of this element per ton of hot metal can increase our coke rate by 1.5 to 2.5 kg. Now coming to the operational stability, which is also no less, and furnace, if we talk about the furnace stoppages, every shutdown disrupt the process. A 1% increase in stoppages time increase the coke rate by 0.5% and decrease productivity by 1 to 1.5%. And burden moisture has been already discussed, and we know evaporating water consumes a great deal of energy. A 1% reduction in moisture in the coke can save around 2.5 kg of coke. The same 1% reduction in moisture in the ferrous burden saves even greater amount, 4.5 kg of coke. As far scrap is using of scrap is concerned, it can save our fuel, adding 10 kg of a scrap per ton of hot metal, decrease coke rate by 3.3 kg, and this is also very important to talk about cooling losses. Heat loss through the furnace shell is a wasted energy, as we know. All and increase of 100,000 kilocalorie per ton hot metal in cooling losses will increase the coke rate by 25 kg per ton. Now, to summarize all what we have discussed uh, in a tabular form, so let's review most important parameters uh, in this way, and here it summarizes what we have discussed so far. And finally, in conclusion, uh, uh, mm, we must have to summarize in this way that achieving low coke rate consumption and high productivity, which was our agenda in beginning of the presentation, it require a multifaceted approach. The permeability is a paramount, and it is improved through a better body quality, control of the cohesive zone, and efficient hot drainage. Or strategic imperatives must be: 1. Maximizing raw material quality. This means higher iron content, lower ash in coke, and strict control over fines. As for the second point is concerned, to optimize blast and injection, we must have to push for highest blast temperature and an optimize auxiliary fuel injection. We must have to see our replacement ratio time to time. We must have to also analyze the dust catcher product, where we have got a fines, and we can analyze their LOI. We need to also ensure operational stability, and in process of maintaining it, we must have to minimize our stoppages and controlling our process variables. We also have to a strict control over hot metal silicon and slack properties to avoid wasting energy. By focusing on these key areas, we can significantly enhance the furnace performance.